This question asks, predict the product of the following reaction. So let's take a look. We are starting with an epoxide, and then we have 1 sodium cyanide, 2 water. So we know we have to be careful with epoxides, depending on whether or not we have kind of basic conditions or acid catalyzed conditions. So sodium cyanide is a C-, and we know that cyanide is a strong nucleophile. So that's going to be kind of under the basic or strong nucleophile conditions for the ring opening of an epoxide. So what does that mean? It means that whenever you have a strong nucleophile, we're going to attack the less substituted side because the reaction is strictly SN2. So we attack the less substituted side, open up the epoxide in kind of like an SN2 fashion, where the oxygen of the epoxide functions kind of as the leaving group. So now we kind of understand the regiochemistry of our reaction a little bit. And then we got to draw out the product and then find which product corresponds to the product that we drew. So let's go ahead and draw everything out. I'm going to add in the charges for my sodium cyanide. And when I look at my epoxide, I can see that this is the carbon that's the least substituted because it has 1 R group, whereas the other carbon has 2 R groups. So we're going to attack the less substituted side. Also very important, we're going to attack on the opposite face of the epoxide. So the epoxide's on the top face. We're going to come in from the bottom face to open this up. So in that case, we're going to have O-. We do not invert the center of the carbon on the left-hand side because it's not attacked. So the stereochemistry stays the same on that carbon. On the other side, our cyanide comes in underneath, and we do invert the stereochemistry of that center. The hydrogen is now going to be kind of facing up, as well as the methyl group that's back. So even though we still have a wedged hydrogen and a dashed methyl, we have inverted that center because they've gone from facing kind of down to facing up. You can kind of visualize that as like an umbrella inverting itself. So let's go ahead and draw the product. After step 2, so we're going to add in water, and that's going to serve as a proton source. So our product is going to look like this, where we have an alcohol and a cyanide, and then the other parts of our molecule. So this is our product. And let's take a look at our answer choices. Well, one big thing here that we should notice right away is that the answer choices are drawn differently from how I drew my product. So this is something that usually is kind of difficult for students to kind of redraw the molecule in a way that matches the answer choices. And that happens a lot because there's more than one way to draw a product or to approach kind of drawing the product of this reaction. So how do I go from the product I drew to the product that's drawn here as my answer choices? First off, I have to recognize what's different. In the products, we have them drawn out so that we have 5 in-plane carbon atoms in each case. So right now, the 5 carbons that are in plane in our answer choices are not in the same plane in our in the product that we drew, because ours are kind of dashed in this instance. So those are the 5 carbons that we need to get all in the same plane, right? So in order to do that, we're going to have to rotate this bond, right? So one thing that you might be tempted to do is to kind of skip this step. You might think, okay, I know the hydroxyl group and the cyanide group have to be anti. And so I'm going to look through my answer choices and I'm going to cross off all the ones that aren't anti. So we're going to do this one, and this one, and then narrow my choices down. But we cannot actually do that, right? Because when we rotate that 3-4 bond, it's also going to change how the hydroxyl group and the cyanide group are oriented to one another. So we can't just assume, looking at the answer choices, that we can get rid of all the ones that aren't anti, because when we rotate the bond, they're going to become anti. Or they might not be anti in the rotated form. They could be on the same face. So if we go about rotating this bond, we are going to want to have our 5 carbons in the same plane like this. And when we do that, it's going to make it so that the hydroxyl group and the cyanide group are actually on the same face as each other. So our hydroxyl group is going to get rotated around so that it's wedged, which makes the methyl dashed. And the cyanide group gets pushed up like so. And so they look like they're on the same side here, even though we know that they added anti to one another. So let's take a look at the answer choices that do match up with this. We have to have the cyanide on the less substituted carbon. So we can actually cross off D and E right away. And if we take a look at this, A is the answer choice that matches up with the rotated molecule that we drew. B would be the enantiomer, so not exactly what we're looking for in this particular case that we drew, although in theory, if we had like our epoxide facing the other way, we would make that one. Okay, and then C doesn't have the right stereochemistry. That would be a diastereomer. So A is the correct choice here. I'm going to take my drawings away and kind of show you how I figured this out using a model. So if you make a model of your product, in this case, I'm going to have this white atom be my alcohol and this green atom be my cyanide group. I'm going to rotate it around here so you guys can kind of see it. So here's the alcohol and here's the cyanide. In my product that I do, we had the methyl back and the ethyl back, just like you can see here. So here they're anti. So in order to really visualize like what product is the actual product upon rotation, it's a lot easier to do this with a model. So I'm going to get my 5 atoms in the same plane as one another. And when I do that, you can see really clearly the hydroxyl group and the cyanide group are on the same face as one another. And so that does correspond to molecule A. So when in doubt, it helps a whole lot to make a model to kind of help visualize kind of rotating that bond.